And now we will start. Welcome everybody. My name is Petri Ehkonen and I'm project manager here at Xiphera. I'm the host of today's webinar. First, let me give a brief introduction of our company, Xiphera. We are a Finnish company founded in 2017. We design hardware-based security solutions using standard cryptographic algorithms. We offer implementations of those algorithms as intellectual property cores, or as we say, IP cores. Our product offering includes cryptographic algorithms and protocols which are optimized for performance. Furthermore, as we design our IP cores mainly for field programmable gate arrays, our product portfolio has implementations where IP core algorithm is optimized for minimal footprint in the FPGA. That's about our products. You can always check our website, xiphera.com, to see more of our offering after the webinar. And now we move to our actual agenda. If the next presentation raises any questions, small or large, please write them to the Q&A section that is located close to the chat icon that you see on the Zoom. We will answer the questions after the presentation. Let me introduce our webinar speaker of today, Dr. Kimmo Järvinen. Dr. Järvinen is Xiphera's co-founder and CTO. Kimmo has 20 years career in academia, where he has done cryptography-related research in various European universities. He has published more than 60 scientific articles, and nearly half of them are somehow related to elliptic curve cryptography, ECC. Kimmo has substantial theoretical and practical experience in secure and efficient implementation of elliptic curve cryptosystems. Please, Kimmo, stage is yours.
Thank you for the introduction, Petri. Today's presentation is about the role of ECC in the post-quantum era, and in particular about what is needed to implement a truly secure ECC implementation and how to use it in a future-proof system together with post-quantum systems. Today's webinar agenda is as follows. First, we will begin by introducing ECC. Then I will talk about certain implementation pitfalls that have led to breaking ECC systems and about what is needed to actually build a secure ECC implementation. In the end, we will discuss the future of ECC, now that post-quantum crypto is coming. The beginning of the webinar will be very technical, perhaps more technical than in any other webinars in this series before, as we take a look into the details of ECC implementations. The abstraction level will again be higher in the latter part of the webinar, where we discuss the use of ECC in the PQ era. First, we will take a look on what actually is an elliptic curve. Then we look a bit deeper into an operation called scalar multiplication, which is the basic operation of every ECC system. And then you also learn what actually forms the basis of the security of ECC. But just as a refresher, cryptographic systems can be coarsely divided into two categories: symmetric crypto and asymmetric cryptography. Symmetric cryptography requires that Alice and Bob, who are communicating, have shared a secret key before they start to communicate. Then the security is based on the secrecy of this key. And a very known example of a symmetric encryption algorithm is AES, which is used everywhere in the internet nowadays. An asymmetric crypto system then again has a pair of keys. So it has a private part and a public part, so that the public part can be computed from the private part, but it is in practice impossible to compute the inverse operation, that is to compute the private key from the public key. And therefore only the private key must be secret and the public part can be shared freely. ECC belongs to the asymmetric crypto, similarly to RSA and also the future PQC. This asymmetry feature that I mentioned allows building many different kind of crypto primitives, but the most relevant ones for today's systems are used for key exchange or digital signatures. So in a key exchange protocol, the communicating parties, Alice and Bob, share a common shared secret, share a common shared secret by combining the other party's public key with their own private key. And then this shared secret can be used for a symmetric method for encrypting or authenticating data. The most famous example of a key exchange protocol is the so-called Diffie-Hellman protocol. Digital signature schemes then again use private key for signing messages, and then public key is used for verifying signatures. And therefore, anybody who has a copy of this public key that can be freely shared can actually verify that this message was signed by the claimed signer. Okay, let's now move to the elliptic curve cryptography part. So elliptic curve crypto has been around for a while. It was introduced independently by two American researchers, Victor Miller and Neil Koplitz, in the mid-1980s. Since then, ECC has become very popular because of its efficiency and small key sizes compared to other alternatives, mainly RSA. The most widely used asymmetric crypto algorithms in today's systems are based on elliptic curve cryptography. For example, elliptic curve Diffie-Hellman and elliptic curve digital signature algorithm are supported by practically all modern crypto protocols as the default option for asymmetric crypto. There are also newer alternatives for ECC. For example, the X25519 key exchange and ECDSA digital signatures. Here on the right-hand side, you see an elliptic curve over real numbers. Crypto systems don't use ECs over real numbers, but these are very good for showing some basic principles of elliptic curves, and therefore we will first take a look on an elliptic curve over real numbers. So the main operation, or the basic operation of elliptic curve crypto is the point addition, and it has a very nice geometric representation. So if we have any 2 points on the elliptic curve, here on in the picture you have P and Q, and you draw a line through those 2 points, then the line always intersects a third point. And if you invert that point over the x-axis, so you can see that the elliptic curve is symmetric in regards of the x-axis. So if you reflect that intersecting point to the other side of the curve, then you get R, which is the addition of these 2 points, P and Q. This also shows the negation. So we consider the point that is on the opposite side of the curve as the negative of a point on elliptic curve. Okay, but as I said, practical crypto systems don't ever use elliptic curves over reals. In practical settings, only integer values are allowed. So we have discrete points, and then everything is actually computed modulo a power of a prime. Here we see a toy example of an elliptic curve with 23 points. So basically, it's pairs of integers x and y in the interval from 0 to 22 that satisfy this equation here in the bottom. You can actually see only 22 points here on the screen at the moment. But there is also an extra point called the point at infinity, which can be thought of as lying infinitely high or low on the y-axis. And that is the so-called zero element of this elliptic curve. So if you add that point to any point on the curve, you get the original point back. Here, as I said, the number of points is only 23, but in practice, we of course use curves with much higher number of points. So here on the right-hand side, you can actually see the number of points on a practically used curve NIST P384. So the difference to this toy example is truly significant. Actually, the number of points on P384 is a 384-bit prime, whereas in our toy example, it's only a 5-bit prime. So you can really see the difference here. Okay, so now if we take one point as a generator from the curve, so in this toy example, we use point 0, 1. And on an east curve, we would use this point on the right in many systems. And now when we start adding G, so first compute G plus G, we get another point using similar formulas that are used on the example for elliptic curve over reals, but of course here we don't have that nice geometric interpretation, but the logic is similar. So now if we compute G plus G, we end up here to the right hand corner and get 2G. Now if we continue adding G always to the previous result, what we see is that we start seeing the result jump over to different parts of the curve in seemingly unpredictable and random fashion, although there is a strict rule behind this jumping. And for example, here we have computed 11 times G, so added G 11 times to itself. And we can continue it all the way to the end. So we can go through all these 22 points that we see here on the screen, and then we end up in 22 times G, which is also the negative of the original point G. Now if we would add G plus negative G, then we would end up at the point at infinity. But the key observation here is that we have actually gone through all of those points without repetition. And as can be seen from the previous slide, the point addition allows defining a scalar multiplication operation on the curve. So we can take a point P and an integer K and get a result K times P on the curve. And it's here called the point Q. The K is typically the secret value in an elliptic curve cryptosystem, for example, the private key. In the previous slide, G was always added to the previous point K times, but actually much faster algorithms are available if K is known. So let's say we have to compute 20 times G. So what we can do is we begin similarly, so we compute G plus G to get 2G, but then we don't compute 3G, but we compute 2G plus 2G to get 4G, then 8G, 16G. And when we have computed 16G, we just add the previously computed 4G to that 16G to get 20G. And this takes only 5 additions compared to the 19 that would be required in a direct algorithm where we only add G every time. And what this means is that we have a fast algorithm for computing scalar multiplications, but actually solving the inverse operation is extremely difficult. So if you know where the point where we started, G, and see the result point Q, it is very hard to find out the value of K if you don't know it in beforehand. So of course, in the small toy example, we can rather easily find out that it is 17 in this case, where the red dot is the Q. But in practical settings, it's impossible to solve. So for example, this P256 curve by NIST gives security that is roughly equivalent to breaking AES with 128-bit keys. So something that is considered impossible at the moment. So what I just explained is the mathematical basis of elliptic curve crypto. And there actually hasn't been that much progress in breaking that in these many decades that ECC has been around. Yet still, many ECC systems that are used in practice have been broken. And it always has been something considering the implementation of the system. So either the algorithm has been implemented incorrectly, or the implementation has not been secure. And now we will take a look on this a bit more closely. So let's say first we'll look what are these kind of algorithmic failures that has been seen, and then we speak a little bit about how the implementation itself can leak information through a so-called side channel and allow breaking the system. So the first example highlights the importance of randomness. So elliptic curve digital signature algorithm, when you sign something with that, you use a so-called nonce value, and nonce means number used once, and the name already tells that it's a value that you should only use once, and next time when you use an algorithm you should choose a new fresh value. So in order to sign a message, or more accurately a hash of a message H, so by using the signing key D, what you do is that you first pick this nonce value K, and then you compute this scalar multiplication that we just discussed, so K times G, take the X coordinate of the result, and that forms the first part of the signature. Then you use that result R and the nonce K and your signing key together with the hash in this specific equation to get the other part of the signature. Now let's look what happens if you reuse the same K for two different signatures. So you have a hash of one message H1 and a hash of another message H2, but you use the same K. So what you have is two different S parts, but in both of them the K is the same, and also of course R, because it's only depending on the K and a fixed base point G, and then we have this signing key which is the same for both. So we can actually just factor out the K value and get this nice closed formula for the signing key D. So if anybody sees two signatures that have been using the same nonce, it immediately leads to a complete break of the crypto system. So now what you think maybe is that this seems rather simple and probably something that never happens in practice, so not a big deal, but actually it has happened in practice. It was behind the famous Sony PlayStation 3 case when it was broken back in 2010, and the reason for that was that they had used a fixed K. Slightly later in 2012 there was also a Bitcoin hack that was possible because of a bad quality random number generator that was used in some implementations. And although the K was not fixed in that case, it still resulted in a break of the system, because the same values were repeating at some point. So if you just saw two signatures that were the same, using the same nonce, then you could break the system. Okay, another example relates to the fact that actually not all curves are created equal. So even if the parameters look very similar, you might have a strong curve and a weak curve. And in many elliptic curve protocols, the other party sends a point, and then the receiving party uses that point together with its own private key. And by sending a point that is actually not on the correct curve, but on some other much weaker curve, an attacker can learn information about the victim's private key. So here on the right-hand side, you see this toy example that we looked at earlier, so with 23 points, and then a much weaker curve which only has 5 points. So those 4 that you can see here on with red color, and then the point at infinity. And the only difference between these two curves is the factor 6 there in the equation. In the stronger case, it was 1. So this has also led to practical attacks. And for example, in 2015, TLS servers that were running a specific bouncy castle implementation had this weakness that they didn't verify that the point was actually on the curve that it should have been. And this allowed an attack which revealed the server's private key after about 3,000 handshakes. So remember to always verify that all points that you receive from outside are truly on the correct curve and not on some other, perhaps weaker curve. Then the third and last example, is a very recent vulnerability from April this year. It's also related to elliptic curve digital signature algorithm, but now it considers the signature verification part. The first step in the ECDSA verification is to actually check that the received signature values R and S are in the correct interval. Unfortunately, a widely spread Java implementation had a design flaw that it didn't actually do these essential checks and accepted an invalid signature with value 0 and 0. And because of how the further steps worked, this resulted in a situation where this R, the x coordinate of the point R was 0, and now this was 0 equals 0, and it accepted actually the signature directly. And if you attach such a signature to any message, this Java implementation returned a valid signature verification result, although of course the signature was not valid. An attacker could have, for example, sent a Google certificate with a 0 signature in TLS handshake and pretend to be Google for a client that was running this vulnerable ECDSA implementation. Okay, so far we have considered vulnerabilities where the algorithm was implemented incorrectly. But even if you have implemented the algorithm correctly, your implementation may still be vulnerable to so-called side channel attacks. And side channel attacks are attacks where information leaks about the secret value are observed by the attacker via some side channel. And side channels could be, for example, computation timing, instantaneous power consumption or electromagnetic radiation, or maybe some microarchitectural features of a processor that runs the ECC implementation, such as cache delays, for example. There are also some exotic side channels such as sound, for example, but we don't consider them further in this talk. Arguably, in my opinion, the timing is the most important side channel because it can be, in certain settings, exploited remotely over the network. And actually, very small amount of leakage can be enough to break the system in certain cases. One notable example is ECDSA. So if one gets to know the length of the nonce K from a large enough number of signatures, that's enough to break a system. And many implementations actually are such that the timing of the computation depends on the length of the K nonce, and therefore the timing may reveal this information to an external observer. Power and EM attacks reveal operation patterns. Many easy algorithms process this scalar K bit by bit so that different operations are computed for 0 value and for 1 value. And now if this operation pattern is revealed with these power or EM attacks, then the attacker can basically read out the scalar that was used from the power or EM trace. So therefore, also constant pattern of operations is very important. Okay, then a few words about our products. So we at CIPHERA have several ECC products in our portfolio. We have already for a long time had IP cores for Curve 25519 related protocols, X25519 and 82519. Very recently, we expanded our portfolio with NIST P-curve, P256 and P384 based elliptic curve Diffie-Hellman and elliptic curve digital signature algorithm IP cores. All of our ECC IP cores are very compact. So those who know FPGAs can understand that they are small when I say that they are about 1,000 lookup tables per IP core. So not much considering the complexity of the computations that is required for implementing ECC systems. Then I want to highlight the security of our designs. So all of our IP cores are fully constant time, so the computation latencies don't depend on any secret values. So they are fully protected against all timing attacks. Also, the operation pattern is constant in these IP cores, and it offers strong protection against power and EM attacks. Okay, and now to the actual elephant in the room that has not been touched so far, because many of you probably know that PQC is coming because ECC could be broken with a large-scale quantum computers. So what quantum computers would allow is to run a source algorithm that will break the basis of the security of elliptic curve cryptography. So it would become easy to solve the elliptic curve discrete logarithm problem that we talked earlier. Also, the RSA will be gone. So integer factorization is also solved by quantum computers. So what we need is post-quantum crypto. And post-quantum cryptography are algorithms, asymmetric cryptography algorithms that cannot be broken with quantum computers. So the underlying hard problem there is such that quantum computers don't give advantage for solving those. And NIST is currently in progress for standardizing PQC. The most promising candidates in this competition are, at the moment, lattice-based algorithms. There are also some elliptic curve-based PQC algorithms, but they rely on a different problem, not ECD discrete logarithm problem, but rather the difficulty of finding so-called isogenies between elliptic curves. So you may wonder what is the role of an ECC system in such a PQ world, and this is something that we will look into next. So the big problem with the new PQC algorithms is the fact that they will be new algorithms. And in crypto, new is not equal to good, as new algorithms have not yet gained the level of trust that we want to have into an cryptographic algorithm. So we cannot really trust that there is not even a classical way to break a PQC algorithm. Indeed, one of the NIST finalists was broken, so rainbow signature algorithm was broken quite completely. So it's not something that is this kind of a theoretical threat that this could be broken, but there is also a non-negligible chance that actually the PQC algorithm, when it's selected, it may later be found to be vulnerable. And for this very reason, many players in the field recommend using a hybrid system in the beginning. So a hybrid system is a system which combines the PQC algorithm, the new PQC algorithm, which provides security against attackers who can use quantum algorithms. And then this PQC is combined with the classical algorithm, in most cases with ECC. And this classical algorithm provides backup against attacks against the PQC algorithm. And for example, the French government agency Nonce has recommended that this kind of a hybrid system should be used, and ECC should be used at least until year 2030. So ECC will still be with us for a long time, and it will not go away immediately when the NIST PQC algorithm competition concludes. So what actually is a hybrid system? So what does it look like? So nowadays, when we use ECC for key exchange, for example, then we have something like this, that we have elliptic curve Diffie-Hellman, and we compute the common secret, shared secret with that protocol. But we don't use it directly, but we input it in a key derivation function, KDF, before using it for encryption or authentication. Now, in a hybrid system, we just add this PQC key encapsulation mechanism in parallel with the old ECC protocol, and then we take the outputs of both of them, concatenate them, and only after that compute the KDF. So not actually that much changes. It's only this additional computation and the input of the KDF. The situation is a bit similar with digital signatures. So nowadays you have a document, you attach the elliptic curve digital signature algorithm signature there, and then when you receive this, you verify the signature on the message, and if it's okay, you accept that. But now in a hybrid system, you also have a PQC signature attached to the same message. You verify both of these signatures, and only if both of them are okay, you accept the signature. Okay, and now I conclude with a single key takeaway slide. So if you want to remember only one thing from this webinar, then it should be this one, that in order for your system to be secure, you must use a secure crypto system. And the security must be achieved both in classical and quantum cases. But in practice, you should use a hybrid system because there is only limited trust in the PQC algorithms in the beginning. So you have to have this secure crypto system. That's clear, of course. But it's also very important to have a secure implementation. So you must implement the algorithms correctly with all relevant checks. It must also be such that it's protected against the side channel attacks that are relevant for your system. So of course, not all attacks can be launched in every system. So you should do this threat analysis. What are the actual threats in your system, and design your implementation so that it is protected against these attacks. And only if both of these, so secure crypto system and secure implementation, are met, your system is secure. Otherwise, it's most likely has some vulnerabilities that can be exploited. So that's what I had to say to you today. So thank you very much for the attention.
Thank you, Kimmo. What a great elliptic curve information package. I like the way you reminded of the cryptographic basic concepts in the beginning, and then you explained the relatively challenging mathematics and the easy to digest form. This algorithm implementation vulnerabilities, they seem to be an ever-going issue. We cannot get rid of those. It seems like that. Finally, I believe the audience got a good understanding that the elliptic curve cryptography has an essential role also in the future. But now it's time for questions from the audience. So if you still have some questions, please submit them on the Q&A box. And let me start looking here. Okay, and there is a first question, is that question raised by the invalid curve case. If I use the ECDSA algorithm, so the Diffie-Hellman, is my responsibility as normal software developer to verify that the point is in the curve?
Yeah, well, that's a very good question. So it should never be the responsibility of the user to check this. It should be always included into the library so that it happens without the user, without any user interaction because otherwise there is always a very high risk that this check is actually not done. So it should be so that whenever you call this, let's say, Diffie-Hellman function, then the function internally does that verification, and if it fails, it returns an error, and proceeds only if the check was valid.
Yes, and so I think it actually applies to any cryptographic algorithm implementation. That shouldn't be responsible for the user, but the implement, whoever it implements.
Indeed. So that's a good design practice to actually put as little trust in the user's skills as possible.
Okay, then there's a question that is the curve 25519, somebody knows the curves, more or less secure than the P256?
That's also a very good question. So curve 25519 and P256 both offer roughly 128-bit cryptographic security level. So they are roughly equivalent in that case. So the ECDLP doesn't have that much difference. But what is actually nice in curve 25519 is that it's much easier to implement in a secure fashion. So you don't have to do this kind of checks so much, and also it has some features that make it easier to implement it so that it's protected against side channel attacks. It's also a bit more efficient, so that's one nice feature of it also.
So there's some difference, not on the security. And then there's
yes, but of course, if you know how to implement P256, it's possible to implement it securely also, but it's just that it's easier with the curve 25519.
Thanks for getting there. So then there's a question that is the hybrid system suitable for IoT networks?
Yeah, let me unmute myself first. So yeah, IoT is of course a very challenging environment for any crypto, and especially asymmetric crypto. So I would say that from a computational perspective, it's not much worse than ECC. So it can be roughly the same. But what is actually typically the case with these PQC algorithms is that the keys are longer and you have to send more data. So in some IoT settings that might be a problem. But then again, the adding the hybrid support, if you already have a PQC IoT device, adding the hybrid support to that, then the overhead for communication is very small because the ECC keys are small. So I would say that the hybridization actually is not all that costly, but it's more question about whether you can implement PQC at all.
Yes, and then I think the next question originates from your vulnerabilities. I didn't know there is such thing as bad random numbers. How I can avoid those?
Again, something. Yeah. So yeah, certainly there are such things as bad random numbers. So if somebody can predict your random numbers, then they are bad random numbers, and you can avoid those by using a good quality random number generator, like the one that we have, CIP 8001B, if I remember the product code correctly.
That's a good point. Then there's a question also. I think this is coming from quite a specialist. Could you maybe tell about supersingular elliptic curve isogeny, or maybe other approaches to make ECC quantum hard?
Yeah, this I already touched this sort of Zicke algorithm in this webinar, so that was just the PQC algorithm that is based on elliptic curve isogenies, and it's still remaining in the competition. It's not one of the NIST finalists. It's so-called alternative candidate, and the reason why it was, to my understanding, why it is an alternative candidate is that it's has even smaller level of trust at the moment because it's very new and than the other candidates, and it's promising in many ways. So the main benefit of CK is that the keys are actually smaller than for other PQC alternatives. So they are roughly equivalent to RSA key sizes. But then the disadvantage is that the level of trust is not as high as maybe for other alternatives in the competition, and also that the computations are quite heavy and it requires a lot of more time to compute than for example lattice-based algorithms. But it's certainly something very interesting, especially for people like me who have background in elliptic curve cryptography. So it's in a way nice that the story of elliptic curves still continues in the PQC domain also.
Yes, so I see that we have still quite a lot of questions there. I think we are not able to answer it timely in time fashion, but we can. If there, so there's more to ask questions, but we cannot answer in the time frame. So it seems that our webinar time is coming to full. So thank you, Kimmo, for outstanding presentation. And also I want to thank our audience for your attendance and your questions. It seems that we have also specialists there. If we didn't have now time to answer your questions, please don't hesitate to send email to Xiphera or Kimmo. You can see the email information on bottom of the slide that is displayed there. And stay tuned, as we will announce soon our next webinar, which will take place in early September. Thank you. Have a wonderful summer and see you all in our next webinar. Bye for now.